Okay, is this working? Am I live? Can I check myself on YouTube? Um, Okay, seem to be talking. Okay, it's working. I can confirm on my phone that it is working and I'm live, which is slightly intimidating because I've not done something like this before. But let's see how this goes. I mean, I don't really expect any viewers, to be honest, but this is really just for my own sanity and fun. And what I'll do is I'll open the comments uh, down here just in case. And I will go live. So, what I'm wanting to build is a 3 engine in JavaScript, my favorite programming language, not really, and build it in such a way that it's super constrained and it is an interesting thing to play with from a technical perspective. I've always been interested in retro computers and that kind of thing, and something I did recently as a side project, just as a technical exercise to take my mind away um, from my main focus at the moment, was to build this ZX Spectrum screen. The way that it works is it reads from an image, which is actually rendered off screen, display none, and there's this canvas and a piece of JavaScript that runs over that image, renders it to the canvas, reads all in the image data, and then it converts it pixel by pixel into a ZX Spectrum mapped screen. Um, and yeah, I've also got another program running over the top of it, which has this sort of mutation effect on the actual bitmap screen, and it mutates random bytes, and that's why you can see flickering all over the place here. Just on that thought, I don't know why I'm mutating the bytes, and instead I could be mutating bits, which would have a much cooler effect, I think, on the overall image here. Because at the moment you just see sort of horizontal lines instead of like individual pixels, and I think it would be a cooler effect to have individual pixels. What I was trying to emulate here was a kind of um, highly radioactive environment where there's some volatile memory on some sort of chip that sits in that environment, and due to their high radioactivity levels, bits are flipped on that in that memory, and thus the overall image is, or the whatever it is. In this case, it's an image that's being rendered from memory, is mutated, and it has this cool kind of like effect. So yeah, what I'm keen to do with this is I'm keen to take this a step further and start building some sort of 3D engine that sits behind the ZX Spectrum screen. One thing that I really have like a vision of building is a kind of game engine, but in this super constrained environment. And I envision it being a game engine which is Web3 first, but it's also all of the memory, all of the state of the game is in super constrained, like 32 kilobytes, 16, 8 kilobytes of memory. And as a result, in order to write and read to this machine and interact with this game, you may have to pay higher prices or whatnot, dictated by the market, whoever's playing the game at that time. and as a result, you might see some really quite interesting behavior. But more of an experiment and something that's been milling around in my mind for quite a while. So to start with, I was just going to start with this, what I built on my website directly, which was this ZX Spectrum screen. And what I wanted to do was want to start rendering pixels and lines and all that kind of thing to this screen. And then I wanted to just do cool, interesting things with it. So I wanted to be able to throw projectiles and have this kind of cool physics that works in this really constrained environment, and just has that real gritty retro feel to it. So yeah, I thought, well, I've got a free Sunday. I've come back from holiday last week and going back to work tomorrow, which is going to be very intense, and really looking forward to the run up to the launch of that game. So yeah, I thought I'd just spend my Sunday. It's got nothing else to do. Building a 3D engine. I don't think it's too complicated. I hope not, especially with the assistance of ChatGPT, which I've already done some preparation here. And I just wanted to see what I could whip out in as short a time as possible. Pardon me. Cool. I've got till 4 o'clock UK time, which is when I'm going to cycle home and have some dinner and relax. Perhaps I'll continue this in the evening if I make some good progress in the next 2.5 hours. Cool. So what I started with was just some really crude matrices and matrix multiplication. Here's just some ChatGPT generated unrolled matrix multiplication. So how 3D engines work is they are actually very, very simple in the sort of core sense, in sort of like drawing dots in a 3D space onto a 2D plane. It's pretty much just a series of 4-dimensional matrix multiplications, as long as you represent all of those vectors as 4-dimensional vectors, which you're then going to render onto the space. So I think we'll start with that. I think what we want is some sort of projection matrix. I think I'll take perspective here and focal length, probably some other values. And it will just be a 4-dimensional matrix, which is a 1-dimensional array, is how I'm representing it. I really thought I'd try and stick to keeping this as simple as possible. If I can, I just have been asking ChatGPT some stuff, and it was very kind enough to generate a matrix, a projection matrix for me here, which should save a little bit of time. 4D projection matrix. Why do we use it for? I don't really care so much about why. I just want the actual. Maybe there's just like a Wikipedia article I can work off. 3D projection, Wikipedia. Looks like there's some interesting stuff here, isn't there? So yeah, like I said, it was already probably one of my most enjoyable projects at university was building a 3D engine. It was a very lengthy project, paired up per project. But it went all the way from the starts, from rendering dots and vectors in 3D space onto a 2D plane, all the way to doing ray tracing and that kind of thing, which is really fun. I don't see this four-dimensional projection matrix, nor do I have the patience to read through the whole article. Just do the perspective projection matrix. Yeah. Sorry, this is not a very enjoyable video to watch at present, but we will get there slowly but surely. I don't want to do orthogonal projection, I want to do perspective projection. Here we go, perspective projection, hello. I'll just find it here, some sort of university lecture slides. F divided by aspect. Already this is different. I have a feeling this is the multiplication of two different vectors. Let's break this out into a separate window. Oh, damn it. Okay, here's one that's similar to the one that ChatGPT gave me. I think what's going on here with these far and near is the clipping planes. The clipping planes is used to remove points which don't exist within the camera's frustum. That's fine. Not quite sure what F is. F is to do with the field of view. So you've got the field of view, camera goes this way. I don't know if this is visible. And then you've got the near and the far clipping planes. And then the aspect ratio is to do with how big the screen is. We can fix that for the ZX Spectrum because we know it's 192 pixels by 256. Cool, so we need to adapt this for our matrix format. What I do really enjoy about matrix multiplication is that you can just multiply these matrices together and you can be left with one single matrix formula, which is super neat. I do like that kind of thing with maths when you have really simple formulas. Okay, so we've got the projection matrix, we've got matrix multiplication. Just double check this is right. So this is the first row. I might as well use the whiteboard. Why not? There's a whiteboard available. Probably best off making sure this is right early on. rather than when it's too late. Cool. Okay, so we've got two matrices. We've got a 0, 0. I don't even know if this coordinate system is correct. It's been that long. And so on, and then we've got B00, B01, B02, B10, B11. And then if we're going to multiply them together, I'm going to have to remind myself how matrix multiplication works, because I have totally forgotten. This is really a beginner's guide, and maybe I was too confident that I could get something working earlier today. So row and then column. Great. Quite like an algebraic example. Here we go. It's quite neat. Okay, I like how that has. Okay, I did use the right coordinate system, although I started at 0 and not 1. But I think using indices is probably a better bet, because that means everything will be spot on then. So I'm going to just rub these out, just make sure it's all correct. I am cutting corners. I'm going to label it 0, 1, 2, 3, 4, 5. 0, 1, 2, 4, 5. And then I know this is going to then be, so C0, we know C0 is going to equal, it's going to be this row multiplied by this column, so it's going to be A0 multiplied by B0 plus A1 multiplied by B4 plus A2 multiplied by B8. And so on. And just to check that that's what we've got here, 2, 8, correct. So this looks about right to me. So if we just go to C1 and do this one shortly, again it's going to be column times row, so it'll be A0 multiplied by B1, A1 multiplied by B5 plus A2 multiplied by B9, and so on. And just to check that that's also correct, so this is C1, and that's going to be 0, 1, 1A, 2, 9. That looks like an A, but it's a 9. Perfect. So the matrix multiplication is correct, as it should be. It's actually not verified for correction because I haven't checked all of these numbers here, but we're going to skip past that. And if there are any issues, you should see some cool quirks with the simulation and the rendering, which is always interesting to see. We have our projection, we have our multiplication. Now what we want to do, take a 4D vector, multiply it by projection, and that should give us our, it'll still give us a 4D vector, but it should exist inside the space. So how is this going to work? Let's have a look. This is probably a good resource to use. Here's another one. Or I could just ask ChatGPT. Try bring ChatGPT over. Okay. So we're going to assume that the camera just lives at the origin. So assuming that the camera lives at the origin, let's just create first vector. Let's just say this is going to exist at this point here, which we probably won't see, and we'll see that that isn't what we expect later on. Okay. To reload this actually. I have a vector of form this. I want to multiply it by my projection. Write code to project it onto a 6 points. I'm just going to copy the existing code that I have. Go. Really don't have to think anymore with writing code, just ask ChatGPT to come up with something interesting. And ChatGPT doesn't look like it's doing anything. What are you doing? Damn it. Oh, it's writing something. It's very slow for some reason. I wonder what's going on. It's annoying that it has to rewrite the existing code. Oh no, it hasn't. Cool. Great. Okay, this is what we want, and multiply that 4 like this. It's already written the code for me to do that. That's what I want. I'm going to call it v4. No, call it call it vec4. M4 multiply vec4, so this is going to have the matrix and then the vector, and it's just doing the multiplication there. I'm going to assume that that's all correct. Eyeballing it, it looks correct to me. And then let's copy this here. In normalized device coordinates. Okay. Let's just output all of them. So let's output the transformed vec. And then the screen coordinates. I have a very annoying build process. Forgive. Let's have a look. Screen coordinates. Yeah, it looks like it's off the screen, which is cool. And here's the transformed vector. Great. I'm just going to create another closure. I'm not going to have a window to unload. I'm just going to do something quite crude. Again, this is just to have something working in the time span I have today. I'm not going to spend my day setting up a new project. Cool, and then what do I want to do now? I want to be able to draw what I'll be doing is I will be doing a query selector, and I'll just do logic log ZX3D. I'm just going to I'll call it ZX3. Don't want that. Convert canvas data to ZX Spectrum format. Don't need that. Want ZX Spectrum screen array. That'll be current ZX data. And this is already a function, so that's good. And I do want an interval. Let's have an interval, and I know there's like request animation frame and all that kind of thing. But I'm not really that fussed on that. I just want something really basic working. The whole exercise of this is not focus on the code and stuff, it's to focus on actually getting something working within these next couple of hours. Reintroduce bytes, kind of. Draw ZX screen data to canvas. I mean, I should really be able to do this myself, animate. And what we'll end up converting this quite significantly as we go on, as we approach building an actual 3D engine that works in like a constrained byte bitmapped environment. Draw ZX screen data to canvas. Animate. So I'll call this one animate here. I want to render, well, basically I want to rotate the point, rotate the camera rather. I want to rotate the camera. Render to the screen. Which is exactly what this is doing. Okay, so I think I can quite easily get an empty ZX Spectrum screen. Looking through this old code. I'm looking for the function where I fetch the image data. Here we go, convert canvas to screen, and from this there'll probably be something in here where it's just generating like a new array. Perfect. Cool. What do I want to call it? What will be quite cool about this once it's all fully set up is that we should be able to like randomize the bitmapped memory, the byte memory, and just render like random stuff onto the screen. Just create chaos, and it should create quite a cool effect. I am mutating this array, great. The joy of mutations. Efficiency, I hear you. Okay. Some good old-fashioned module pattern. Get empty ZX screen. To me. Okay. Why not rename it? Okay, so we've got our empty screen data. Really, the first thing is just rendering it. Cool. Let's try that. I'm just going to create a new canvas that sits above my old one. Oh, there's not a comma there. Why? I guess I don't need it. Don't need a source parameter. ZX3. Wonder what the football scores are. Leeds are playing Norwich in the playoffs. Empty ZX screen is not defined. Nout. Which is expected, right? Let's draw it once per second. Great. So we are actually drawing something to the screen to the right canvas by the looks of it. So we want to project the point to the screen. First, before all of that, draw a sample point. And that'll come after the projection. So what I want to do is I kind of want to work backwards from having the actual screen data to now projecting a point onto the screen. The way I'm going to do that is I'm just going to look into some of the functions I have here, and I'm sure some of them are for like drawing to the screen. Or maybe not. So we have an index. Y multiplied by canvas width plus 4. A lot of this is redundant that I'm using. So this is functions for converting canvas to a JX screen. So this is kind of like what we're looking for, although this index is on the wrong coordinate system. This is actually looking at image data, which we're not really that interested about. Kind of want to go the other way. We want to draw onto the screen. So this is convert the canvas to a ZX screen, getting the image data, it's getting image data, and then for each element here, display screen. Canvas to ZX screen. Look through each 8x8 block for attributes. So this is not just canvas to ZX screen, of course, this is the actual code for converting an image. I'm wondering, my phone needs to be charged. So I had lunch. Sandwich is sitting there. For some reason I'm not eating it. I'm not sure why. Just not that hungry. Look through each pixel in the 8x8 block. So in each 8x8 block. I kind of want to just like get a coordinate. Oh, here we go. The function does exist. Get screen indices. I should have called it indices instead of indexes, but here we are. Nice. It also gives me an attribute index, which is really nice as well. The annoying thing though is I still need to then mutate that point in the image data. Kind of want to just have like I want to be able to render it on the screen, but I'll tell you what, I'm overcomplicating this. All I need to do is really draw a number 1 on the screen. To do that, I just need to export this function. And then here, draw the point by ZX screen data, not attribute index. I think it's pixel index. I'm just byte index. I'm just going to call it byte index for now. We'll see if it's right later on. Is equal to 1. Let's just do 0 to 0. Pixel index. Test and remove this. Syntax error. Missing comma. Yes, I have no linting or anything on this Vim. A bit silly. Everyone uses VS Code these days. All this just comes out of the box. You install the right plugin. Happy days. It's okay. Okay, doesn't look like it's really done anything. That's fine. So let's get the attribute index and let's set the attribute index as well to 1 and just see what that does. I don't know why I'm doing it like that. There we go. And it has drawn a pixel. Great, so it's blue. It's going to be blue by default. Now what we can do, which makes me guess if I set this to 255, the pixel should move to the left. It's drawn a line, of course, it's filled it in, so therefore 128 should be a pixel on the furthest left. Nice, I think it is, I think that's right. Cool. Okay, we're actually getting somewhere. It's taken a while. So I don't really need to remove this for now. I might just put the pixel somewhere in the middle of the screen. No, I'll leave it in the far left. And I'll set the attribute. Let's just try 3 instead. Let's see if that gives us a bit more of a juicy colour to work with. Okay, that's more visible. Probably wasn't visible on the live stream before, but now it should be. There's like a pink pixel in the top left. Great. Cool. let's project the point to the screen here. Did it further up, but we'll remove that. Screen coordinates. So what can we expect from screen coordinates? We expect something like this, which I would think we would really want to clip. And maybe this is where ChatGPT comes in. How can we test the transformed vec to check to see whether it is within the frustum, and therefore should be rendered. I think it's a frustum, isn't it? Frustum, something like that. You need to check to see whether you need to determine if the vector coordinates fall within the defined minus in the clip space. The clip space is a special coordinate system where if a point falls within the range of this for each of its x, y, z components, it's considered to be inside the frustum. If any of these points fall out, it's outside. So within frustum. Here we go. Exactly what I wanted. What I am tempted to do now is I'm actually tempted to have an array of points, like a point space. Call it vector space. So it's going to be an array of these points, and therefore we can just we can add to it what we want. Move this up here. I don't know whether to do like a crude functional thing. Let's do it. Filter is within frustum. And then we'll do the classic. What I'll do is I'll just highlight the whole row just to show that it's in the space. So we've got screen coordinates. Project screen returning XY, which we might as well just do as XY, and then we can just do an XY here. And then we can do this. Now what I'd expect running this is that it'll no longer get to this point because the coordinates will have been not be visible, basically won't be visible inside the frustum. That's fine. The next goal now is to create a rotating camera. And once you have a rotating camera, we should at least get the points within the field of vision at some point. And at that point, we should see the line drawn across the screen, and we can tidy all that stuff up later on. I'm going to do mutation again, so I'm going to do camera. I'm going to ask, can you give me a camera position and orientation vector? Not sure, I can't remember how this works. How would you represent the camera's position and orientation? Then how would you apply that to the objects within the scene? Can you provide this? Let's just run with it. Short answers, please. Don't want any long running thing. Start using a sandwich. So I want a quaternion for the camera. Objects within the scene to eventually point within the space. It's a bit annoying that TrackGPT's like gone back to using classes. I was just going to use like raw arrays to represent this. To be fair, I'm probably just going to start off with the identity matrix. And then start multiplying from there. Might do some stuff. So we always have column vectors. And then we multiply by the rotation vector on the right-hand side. And I remember the kind of philosophy behind it was to map into its coordinate space. So if we wanted to map a vector into another coordinate space, the philosophy is multiplying it by some matrix to put it into a new coordinate space. Each vector is effectively a coordinate space, the definition of a space, a transformation of something. So let's say we've got V multiplied by A. That gives us a new vector V prime. We can get back to V prime by multiplying each side by the inverse. This is where the whole eigenvector thing comes in, I think. So we need to know how to go from, what is f? So f takes an a and returns an a prime. F is what? We need to know what f is. That's the inverse function. I'm going to call it inverse. That's going to be useful to us. But what's our core objective here? Our core objective is to take a vector and multiply it by a camera in order to get it into its space. Is any of this correct? I think we multiply the other side, don't we? Chaos. A V equals V prime. V prime is equal to A inverse V. No. V equals A inverse V prime. To take xy. Let's say we have some rotation matrix R. Forgot how sort of headbanging this is. Should define a coordinate system. So Z is always forward, X is right, Y is up. That might help. Showing it more weirdly. I want a rotation matrix. Here we go, here's some rotation matrices. 4D. Remember why I had to take lectures for this. So really, in this case, we're actually only interested in rotating along the y-axis. To do that, we need this rotation matrix, which is cos y 0 minus sine y 0 0 1 0 0 sine y 0 cos y sine 0 cos y 0 0 1 0 0 1. So I have this quaternion, which is the identity matrix, which currently describes the camera's position. And this is going to be the vector in the vector space, in the camera space, sorry. Let's say we want to move the camera clockwise. So camera initial is going to equal to the identity matrix. So initially point V assuming the camera's just looking forward. Interesting. Deep think. So I have a point V in a normal coordinate system, but I want to go to the camera's coordinate system. How do I get there? I'll simply multiply it by the camera. But let's say I want to then rotate the camera. What do I do? It's been a long time. Draw a helpful 3D diagram. It's not great, but it'll do. Let's say I want to rotate the point. Translation. We also want translation, don't we? Let's just have that on the board. Okay, so it's just the identity with the coordinates you want to translate to. 0, 0, tx, 0, 1, 0, ty, 0, 0, 1, tz, 0, 0, 0, 1. So if I want to translate a point, tricky. Let's do an example. Yeah, this coordinate system just makes sense because that's going to end up being plus tx v1 plus ty v2 plus tz and then 1. 1 plus 1, which is 2. No, it's just going to be 1 because you're multiplying them together. Nice. Neat. So, so we have a translation that's translating a point. But let's say I want to translate a camera. Let's replace the point with a camera. And let's call this t multiplied by c is going to equal a new camera position translated. And assuming that the camera is at the origin, the way that we get back to the origin is we multiply the inverse in order to get C, which is the original camera position. I'm going to redefine this as identity here. C. We're going to have T, let's call it C for camera, is going to give us the camera position, but then in order to get back to the identity, we have to do T prime C multiplied by C, which is a current camera matrix. And then how do we apply a rotation matrix? Rotation matrix. I'm assuming it's the same kind of multiplication. Yeah, you apply it before the vector. Cool. In addition, you want to rotate first because you want to rotate around the origin. So you start with a TC and then an RC multiplied by the identity will give you the camera. And then let's say you want to get back to the identity coordinate system. You then have to do R prime multiplied by T prime by C. So I wonder if I is equal to R prime C T prime C T C R C. It is, but then is matrix multiplication transitive? Is that the law? Ah, it's been 4 years, coming up to 4 years since I ever did this. So it's all being relearned. Is matrix multiplication commutative? If the diagonalizable and commutativity is can you provide an example? Can't spell today. It's fine if matrix multiplication isn't commutative. Because wrong way around. Now I'm just hoping it's actually easy to invert a matrix. Oh no, the determinants. Cofactors. Ladies and gentlemen, we've entered hell. wonder if I'm complicating this. I swear there was a way of easily doing this. Just got carried away in four-dimensional space. I mean, this could be any number of rotations or translations. Oh no. It does look nasty. Obviously, adjustments need to be made. I'm now curious whether I've got that old 3D engine. Probably in my computer science stuff. See. Here we go, comms, computer graphics. I do have it. Huh, matrix inverse. GLN. Wow, there's a lot of code. And I think the complexity of this has like grown quite significantly. If I did have all the formulas out of the box, it would be quite nice. Oh my goodness. It's not satisfactory, is it? It's a lot more painful than I thought it would be. Inverse of an orthogonal matrix is just its transpose, like translation matrix. I wonder if it's also just its transpose. Shall we work with that assumption? What is, I'm going to move to ChatGPT 3.5 because it's quite slow. What is a orthogonal matrix? For the translation and rotation matrices orthogonal, and if so, what is an orthogonal matrix? For the translation and rotation matrices orthogonal, if so, can I just transpose the matrix to get the inverse? Translation matrices are not orthogonal. I might end up going for the slow option here. What happens I multiply this. Well, if I multiply it by the end identity, it will just equal itself. But I want the inverse. I guess it depends on the order. Zero, zero. What about this one? Tx. Yeah, it's not going to work the way that ChatGPT is suggesting it. Rotation matrix inverse is just its transpose. Well, I certainly need a transpose function, so I might as well write that. Transpose and then inverse. I can do this myself. Oops. M0, M1, M3. that right? Of course it's not right. That's correct. Got the transpose function. It's like a point drawn on the screen before the end of the day. How do I do it in verse? Let's just do a crude inverse. It is getting it wrong. Because that should be 12, that should be 3, 7, 11, 15. Instead it's gone 12, 13, 14, 15 on the bottom. I do like this inverse though. It looks well good. This is just going to have very crude testing. I'm a bit confused why it chose the bottom for the translation. What gets applied first? The translation. Oh. What gets applied first? Is it the translation or the rotation? It's the rotation. But if you take the inverse, then it is translation, inverse of rotation multiplied by inverse translation. It's going to be interesting to see how this plays out. Okay, let's just see if that works and there's no syntax errors. Is within frustum. It's not defined. It's not defined indeed. I think my headphones might have run out of battery. Within frustum. So let's bring that back. What am I doing? Wrong way. It's within frustum. Cool. Ah. Okay, let's just try that now. Just do a good old-fashioned. Okay. It thinks it's within the frustum, but it's not because it's not projecting it. Actually, no, it's not. Sorry, I got that completely wrong. It is filtering it. We kind of want it just in front of the camera, so x coordinate should be 0. Y coordinate should certainly be 0, and then the z coordinate near the far, so that's 1. Testing, 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 testing. Am I back? I think I am back. Impressive. Great. Also doesn't appear. Key. I'd like to remove this filter just for the sake of being able to see what it's actually doing. Transform vector is not defined. What have I done with it? First spec, of course, is not defined. Should be vec 4. Screen coordinates is not defined. Oh, it has drawn it to the screen. Nice. Slightly off center. Cool enough. Cool enough. If I remove the filter. Before I do refresh though, yeah, apparently it's not within the frustum. Coordinates out of bounds, oh dear. Nothing is within the frustum. We don't have any rotation vectors yet, so let's just import for rotate y. Looking around at the whiteboard. Math.sine theta. Math.cosine theta. Oops. I'm just going to translate this. Translate. It's a non-orthogonal matrix. Okay. Cool, so I kind of want a tick, something that I increment on each animation loop. Start on 0. Well, we'll start off with the identity. And then we're going to multiply. First we're going to multiply inverse, and for inverse camera. Camera is going to be equal to multiply, not vec4, yeah, vec4 there. Rotation, then translation. Rotation y. Theta.
I think we'll keep it as just a rotation for now and see what happens. Just kind of want it like a lighthouse. I don't really need the tick anymore. I will need it though. I might need it. For rotate. Let's have a look at the position. Yeah, I'll definitely need the tick. Let's divide by 10. I want to move the camera back. -1 on the Z. And then I kind of want it to just like spin like a lighthouse, -5 even. But we could have the camera move back with each tick, to be fair. Let's do minus tick, because that's just going to do big jumps back, which should be interesting. Let's get rid of this camera and just have a const camera here. I've already got that. And then I kind of want a camera coordinate. Position is going to be equal to console.log camera position. It's going to be supply vec4. And for inverse of camera. That's not what I want. That doesn't look right to me. Oh, it does. It's a bit odd for a start. So maybe we'll get rid of the rotation to start with and just have the translate backwards and see if the inverse works with that. Like I said, this is just, it had no testing. It was very likely going to be issues with it. I think I multiply by the camera, not the inverse. Yeah. And that gets me the camera coordinates. So the camera is now stepping backwards. That all seems fine. Where it seems to start to go a bit weird is when I start multiplying the camera's position. When I start to rotate the camera. Let's rotate it. Let's just rotate it now. So we have no translation. We just rotate. Yeah, and the camera's staying at position 0. Now I want to know where like a specific position is, so let's say the point in front of the camera. This should be in front of the camera. And for inverse camera, okay. So it shouldn't move on the Y. So if we're moving theta on the Y, then I'd expect the point to change on both the X and the Z, correct? I mean, at a glance, that looks fine. Doesn't seem to be any oddities. Let's just check the translation to be sure. So camera position. Am I doing the right one here? I'm not. Ah, yeah, I'm doing the right one. I'd expect the point to sit further and further in front of the camera. Great. Okay. Cool. The point is further ahead. Thinking. Close to having a basic version of this working, it just doesn't seem to be wanting to appear on the screen. So after the inverse is applied to the point, you then apply the projection matrix. Multiply, very crude multiplication. So the projection should stay relatively the same at 0, 0. Cool. What about if we move it slightly on the x? Probably needs to be normalized. Not quite sure. I think this is where I'd expect the projection to kick in. Z within the frustum. And then I think that brings us within minus that, which is within the -1, 1 range. Same for the Y, not sure about the Z though. No, the Z's out of range, that's why it's failing the frustum check. Why should the Z be out of range though? Where's the near far coordinates? Near 0.1, far 1000. Field of view. It's a wide field of view. So near plane, far plane. Bit odd. Because I would expect Z to check the far point. Let's check. Here we go. I have a feeling it's inverted the wrong way. Maybe not. R plus L. Got 15 minutes to wrap this up. To be fair, there could be a complication with how I'm calculating the camera inverse. There could be a bug there. It's quite infuriating, this one. So specific T tokens in the Z coordinate is essentially based on the common conventions using graphics APIs. The Z value of transformation points will not be normalized to -1, 1 range typically expected in the NDC for CL, so the range will be transformed due to how the Z values are calculated. Place them in the range from 0 to -1. -1 to 0 then. Cool, it's very smart to pick that up. Oops. And nothing is being drawn to the screen still. Am I missing something? I mean, that shouldn't make a difference anyway. This check is just a bit tighter. Can put it 0 for now, but of course it's not going to make a difference. So why is it always just out of range? It's got to be something to do with the normalization of the vectors. But I think from what I see, the test point is normalized, it's 1. Huh. And for inverse camera. I think I've complicated it a little bit by this check, because now the point always seems to be on the other side of the near-far plane. It could be a result of the projection matrix being wrong, or some other translation. I mean, looking at this, the x coordinate would be very negligibly negative, which means it's slightly just to the left of the centre of the screen. However, the point itself is at x1, which is correct. You'd expect it to be slightly negative. What I don't understand is how the z is way off, really. The z clipping plane. Yeah, it's a bit of a funny one. Because this expects it to be negative or 0. And it's just confused me, and I think this is why you just don't rely on ChatGPT. You understand all the bits and bobs. We don't really have enough time to understand all the bits and bobs. So, yeah. Thinking on the spot, I think we're going to have to just change but why would the z be? Still doesn't make sense to me. The z gets multiplied by the projection matrix and then it ends up in front of the camera, but it's not doing that check. It's ending up just slightly too far ahead of the camera. But why? But why? Why? It's ending up slightly just too far in front of the camera. And that I do not understand. And that I do not understand. Am I applying the projection matrix properly? I need a demonstration of how to apply this projection matrix. I want the exact same matrix as I've got. So the one that I've got is this one. Which is exactly the same as this, except it doesn't have the near far stuff on it. I'm wondering if there's another one. Oh, this is exactly the same one as mine. doing his coordinates. It's writing out matrix multiplication. So there's a point in 3D space. Have I messed up field of view? Or is it already doing that? No, it is already doing the correct thing there. Aspect ratio. Field of view. That gets your projection. And you've got your point. X, Y, Z, W. And then you've got your projected point. The projection matrix multiplied by the point, which is what we've done. Although we've done the camera transformation within there, but albeit that checks out. And then we just check to see whether it's within the frustum. if the camera is just looking the other way by default. In which case, if I move the camera backwards, okay, I'd expect it to pass the, is it within the frustum check now? Still doesn't seem to be the case. Eyeballing it, it looks correct. It's a pain, isn't it? No, it's not correct because it's still thinking that the camera the frustum check insists it's between -1 and 0. I'm just a bit odd. Okay, now it's drawing. Now it's drawing. Cool. So we've got something working. At least seems a bit wonky. So the camera's looking down the negative Z axis. And we're now moving the camera forwards. It's still looking backwards. I mean, 4 o'clock now, we've just got to the starting point. Once we can start drawing stuff on the screen in a cool coordinate system, we now can start, we now have something like quite interesting to work with. It's a bit of a shame that this is how far we've got. Transformed vector. Transformed vector. And then projecting to the screen. It's a bit odd how it's not like right in the centre of the screen. It's like at a weird point down there, which is not what I would have expected. And to be fair, this is still the test. Oh no, it's not. The test is in the corner, the top left, but this is the actual 3D drawing. So project to the screen. I think it's 192 by... Oh, I got it wrong. It's the wrong way around. That's quite hilarious. Probably a reason for the weirdness. No. Oh yeah, in the middle. That looks more in the middle anyway. It is. I'm going to accept that as a victory. After I've drawn it to the canvas, I'm going to reset screen data. But this should be drawing a cube. Should be drawing a cube. It's not. It's drawing a point. Coordinates are still out of bounds. This is why it just a bit confuses me just a bit. Screen coordinates. Yeah, I mean that's not within the frustum, is it? So I don't know why it's getting there. camera's stepping forwards, but Vec 4's not changing. Because I'm applying the projection matrix twice. Could explain some of the weirdness. Okay, it looks like these are within the frustum. Well, this 1, 2 coordinates, whatever it is, are within the frustum. Test point projection. Filter is within frustum. Is within frustum. I mean, to be fair, the test point isn't in the frustum. Let's get that right. Test point is now again for the old reason, not in the frustum. Test point projection is now in theory within the frustum. This might be helpful. This might be helpful. Okay. It's 2. Could be better. Good. Oh dear. That is not what I'm after. Okay, I don't think this is any good. Tesseract Explorer, absolutely not. Absolutely not helpful. It's cool though. So identity to start with, and then quite difficult to visualize. First row, second row, so it's the Z. It's here, increases. Which means the camera's marching forwards. Inverse should just be -2 there, yeah. But we've already established that this is all fine. And then it just seems to be the projection that's playing up. Test point in camera space should be, yeah, and as we go on, as we step. The test point hasn't moved. Test point hasn't moved. Is that right? I think this is... Camera position's not changing. Because coordinates is out of bounds, that's why. That should be clipped by this within frustum. Oops. Drawn to screen. Okay, this is better, but we're kind of back to where we were before. Camera position Z is 9, so the camera's marched forwards. This is the camera matrix. This is the inverse camera matrix. The test point camera space. Cosine 1 sine 0. Still outside of the frustum. I cannot work it out. tangential. I wonder if we try different orientations, though we should be able to figure out the orientation of the camera. The camera is now stepping back again. Stepping back on the Z. Here it's looking down the X. So here it does look like it's looking down the negative Z, which means it doesn't need to step. Forwards. Not really getting anywhere here. I'm not quite sure why it doesn't just work out in the box. I mean, after projection the test point, and after projection it ends up at .01. Yeah, completely puzzled. Completely puzzled. surely it can't be anything to do with the planes. I mean, it's well within that definition. I don't know if they're being transformed at all somehow. Let's have a look at the test point projection. Still not within the right space. Totally puzzled. Focal. Let's move this into here. What's the problem with this though? This is why you do the maths. It all makes sense. This does not at all make sense. I just need a formula that works. Just need a formula that works. And I have a feeling I'm thinking of something slightly bogus by ChatGPT. They're all different. Which is the one I'm using? It's this one. I'm getting a divide by zero on some of these, which is problematic as well. Okay. I think coordinates out of bounds. Very confused. Spinning on this. Makes sense. We're not being fobbed off here by these frustum calculation. Problem then is it's going to say it's out of range. Coordinates out of bounds here. Sure the camera's pointing that expected way, or negative Z. might help. Yeah, it's way off, isn't it? Doesn't make a whole load of sense though. I think it's not normalized. Okay, that's definitely more promising. Definitely a lot more promising. And then eventually they were all within the frustum. However, now nothing. Screen coordinates. transformed vec. Aha, it works. We have a cube. Phenomenal. Now let's rotate the camera. Let's go a bit faster. That looks right. That looks very good. I think we've got something working. Aha. Where's the point space, vec space? Vec space, vec4 space dot map. So we've got a test point. Now we're going to multiply vec4 by test point. Sorry, my brain's now running slowly. Let's make it rotate. Get rid of the test point. So that's test points. Cool. It's spiraling into chaos. I mean, we've got something. This is great. To make this even more slick, you can do an M4 multiply vec4 translate minus 0.5, 0.5, 0.5, so I'm just going to center the whole object and then rotate it. No, you'd have to do the centralization earlier. Vec4. You want to do it once. There it is. I can probably more elegantly make it rotate slower and make the camera move back slower. Oh, that's really cool though. That's really fun. Cool. Eighteen, 19, 20, 21, 22, 23, 24, 25. It seems to be spinning faster. I don't know if that's just the JavaScript engine able to render stuff more quickly. Move this. Drawn. Or whether it's like overwriting itself. Yeah, that's what it's doing. Yeah, it can't mutate the global. Okay, that should be more sane now. So it's just a multiplicative effect when it's spinning. Much cooler. Much cooler. Although now it's spinning very, very slowly. Yeah, very cool. I think we'll wrap up there then. Not really much more to do for now. I think next time we'll focus on shading, or even just drawing lines to start, wireframes, and then move on to shading later on. Fun times, fun things.